Okay, so 2008 E1, we have a metal sphere of radius A, has charge positive Q. It's surrounded by an uncharged, so no charge on that outer shell, and it's metallic, which means that it's a conductor, with inner radius B, outer radius C, as shown above. And we want to express all algebraic answers in terms of the given quantities and fundamental constants. Part A, determine the induced charge on each of the following and explain your reasoning in each case. Okay, so we have this charged sphere on the inside, and then we have this conductor on the outside, and we know that charge on a conductor is allowed to move freely, and so what we're going to see happen is the negative charges are going to want to move on the inside of the shell so that they can be close to the charged sphere, and then the positives, so there's going to be a net positive left on the outside of the shell. Okay, and we want to figure out what are those charges? How much charge is on the inside? How much charge is on the outside? Okay, they will ask this question. Um, it's a pretty common question. The way that you deal with this is you draw Gaussian surfaces in different areas. You want to draw them in areas where you already kind of know what the electric field should be. Okay, and so we are going to draw. So we want to figure out the inner charge and then the outer charge. So let's call the inner charge Qi, and then we'll call the outer charge Qo. We need to figure out what those are in terms of that positive Q right there. Okay. So let's see. Let's draw a Gaussian surface, and I'm going to pick this surface right here. I'm going to pick a Gaussian surface that is inside of the conductor. Okay. Why am I picking that Gaussian surface? Because I know something about that Gaussian surface. I know the electric field inside of that conductor, right? E is equal to 0 inside a conductor. Okay, and so for part A, we're going to apply Gauss's law. So closed integral E dot dA equals Q enclosed over epsilon naught. Okay, and we already know that this is 0. Okay, if the left side of the equation is 0, then that means that Q enclosed must also equal 0. Okay, so what does Q enclosed equal? It equals all of the positive Q, all of positive Q, plus Q sub I, Q inner. Okay, and so then we can solve for Q inner. Q inner is just equal to negative Q. And that's it for part A. Okay. Part B, there's different ways to think about it. You could draw another Gaussian surface and you could do a little bit of work. But here's what we know. We know that the conductor as a whole is not charged, right? They tell us surrounded by an uncharged metal shell. So what that means, I guess this is part 2 of part A. What this means is that Q of that outer shell is equal to 0. What is that equal to? It's equal to Q inner plus Q outer. And we already know what Q inner is. It's negative Q. So what must Q outer be? Q outer is just equal to a positive Q. Okay, so we have Q outer is positive Q, Q inner is negative Q. Part B, determine expressions for the magnitude of the electric field as a function of r, the distance from the center of the inner sphere. So we want to know what's the electric field when r is less than a. We want to know what the electric field is when r is less than b but greater than a, and then when r is less than c but greater than b. And I guess for part 4, it's probably when r is greater than c. I guess they forgot. We'll just do that anyway. I don't know what they mean there. So when r is greater than c. and then we're going to graph it for part C. Okay, so let's start with part 1. Okay, so a lot of times you might look up the scoring guide for this, but a lot of times you get a point altogether for just writing down Gauss's law at least one time. So for part B, I would just start with writing it down. E dot dA equals Q enclosed over epsilon naught. All right, so part 1 is when R is less than A. Okay, this is really important. They tell us that that metal sphere in the middle has a radius of the metal sphere in the middle. It's metal. I don't know what I'm trying to say. It's metal. It's a conductor. So what does that mean? That means that the electric field inside of that thing is 0. So you can just write E equals 0 because Q enclosed will equal 0. I don't think you need to explain yourself, but you should just be able to write E equals 0 for that and get points for it. All right, so part 2, this is when R is in between A and B. Okay, you can apply Gauss's law and figure that out. It should look just like a point charge, though. Okay, so if I apply Gauss's law, I pick a surface. Let's say I pick, we'll use a different color. Let's use that color. Okay, so if I pick a Gaussian surface, I want it to have a radius of R that's in between A and B. Okay, so there it is. And I'm going to do closed integral E dot dA equals Q enclosed over epsilon naught. How much charge is enclosed? Just Q. Okay. Left side of the equation is going to become E times the area of the Gaussian sphere. Okay. E of this, the area of a sphere is 4 pi little r squared. So that means that E is equal to Q over 4 pi r squared epsilon naught, which is the electric field of a particle, charged particle. Okay, part 3. Part 3 is when the radius is in between B and C. We already said something about that. We said the electric field was 0 because it's inside a conductor. So no work needs to be done here. Electric field is 0. And then part 4 is when the electric field is, or when the, we want to know what the electric field is at a point R greater than C. Okay, so if you drew another Gaussian surface, this one would be all the way out here. Okay, and it has a radius of, that's supposed to be a sphere, by the way, radius of R. Okay, applying Gauss's law to that again, I think we're going to get the same answer as part 2, it looks like. But we have closed integral E dot dA equals Q enclosed over epsilon naught. How much charge is enclosed? Okay, well, the outer shell, the outer conducting shell has no charge, so 0 for that plus the plus that middle charge. So nothing here, but we do have that positive Q in the middle. So we're going to get the same exact thing, same exact expression. So this is Q over epsilon naught, and so we have we'll get the same thing. You can do the work if you want to convince yourself, but we get E is Q over 4 pi r squared epsilon naught. Okay, last thing we need to do is graph it. All right, so looking at our graph, I haven't checked the scoring guide on this, but I'm guessing you get a point for each section. Okay, the 2 easy sections is between 0 and A, and then between B and C. All right, so let's use, I don't know, let's use that color. Let's make it a little bit more bold. Okay, So between 0 and A, the electric field should be just a straight line on the 0 mark. That's not very straight. It's okay. Okay, and then between B and C, it should be 0. From A to B, and then from C on, let's figure that out. Okay, so here's the here's what we have when R is greater than A and less than B. We have E is equal to Q over 4 pi R squared epsilon naught. Notice that E is proportional to 1 over R squared, which means as R increases, E should decrease exponentially. Okay, and so that graph should look something like this. Okay, and then from C on, it'll look the same, right? Because we got the same formula. But since we're at a further distance already, that graph should start out a little bit lower. It should start out a little bit lower. Okay, so I think it should probably look like this, and then it should tend towards infinity. I'm sorry, it should tend towards 0 as R tends towards infinity. So it looks like that. Okay, and that should be the graph for that one.